Okay, so chapter 12. This is the last chapter we're going to get to. We're going to keep working with that idea of relations. We're just going to talk about a special type. So here's a definition. A function is a relation F that's a subset of A cross B, right? Remember, relations are, okay, subsets of Cartesian products, such that, well, what was the rule you were told about functions? We can draw this off to the side here. Back when you were in, why is this having issues? Oh, sorry. Back when you were in high school. Yeah. So yeah, it was kind of that vertical line test. Can't have more than one y, right? To match with an x. So we're going to need that rule. We're also going to need the fact that the function has to use all of A, okay? All right, so such that for every little a in big A, there exists a unique little b in big B with A, we'll do it this way, ordered pair AB, an element of F. All right, so you see that means I have to use every single element of that first set, which you know is called the domain for a function. You've heard that word before. That's in the next definition. And every single thing there gets one unique B assigned to it. Now, that does not rule out, so we'll say like f of x equals x squared is okay. So here's what we're saying. If I take from my domain, let's say I put in 1, what does it output? What's its matching y value? 1. Will it ever have a different matching y value for that function? No, 1 squared is 1, right? Notice that -1, 1 is also in that function. That's okay. It doesn't say the values from B aren't allowed to repeat. All it says is once you pick something from the domain, it only has one thing it's matched to. Okay, you guys see the difference? Okay, so we have domain. That set A is called the domain, often notated dom or dom lowercase or capital F. Then we have set B is called the codomain. So the range of F is the set of all B in capital B such that there exists A in capital A with a B, an element of F. So the range of F is the stuff from B that's actually used, okay? Some books will combine that word range and codomain and just call them both range, and you just have to use context clues. Your book, okay, uses codomain to mean the potential outputs, right? And the range are the actual outputs you use. So for example, sine of x, right? Potentially could output any real number, but in actuality, it only outputs between -1 and 1. Okay, so that's the difference we're talking about. All right. So let me do some notation stuff. Sorry, I'm bouncing around there. So with relations, right, I could write, like I have been, A, B, an element of F. I could say A, put the F in the middle, B, like we've been doing. But with functions, we use this special notation you're familiar with, the f of a equals b, okay? Those all mean the same thing. So why didn't we use that last one, that last notation that you're used to for generic relations? Well, let's see. So let me make one up. So, and it doesn't have to be complicated. Let R equal ordered pair 1, 2, ordered pair 1, 3. That's a relation, okay? It's not a function, right? Because given an A, I actually have two different outputs that match it for one. It doesn't just have one thing that goes with it. It doesn't have a unique thing. So if I try to use that function notation and I say R of 1 equals, what the heck do I put, right? Do I put 2? Do I put 3? That doesn't make sense, okay? So that last notation only works if it's a function, only works if given an input, there's one exact output, okay? That's why we need that in order to use that notation. All right, so just a comment. See, the range of f is a subset of the codomain, okay? So a well-defined function, you'll be able to tell, okay, at least your potential range elements. All right. Technically, the empty set qualifies as a function. Let's look back at our definition. To be a function, it has to be a relation. So it has to be a subset. Well, the empty set's a subset of everything, such that given anything from the domain, there is a unique B. If my domain's the empty set, then the empty relation is a function. But that's kind of silly. So we ignore that possibility. Okay, we're going to assume our functions have actual values to them. All right. Since functions are relations, that means they're sets. So they're equal if their elements are identical. Okay. So, you know, if function f is, I don't know, ordered pair 1, 2, ordered pair pi 3, and function g is ordered pair 1, 2, and ordered pair pi 3, those are the same function because no matter what I input, 1 or pi, I output the same thing. If I input 1, I output 2. If I input pi, I output 3. Okay. That's what we mean by if their elements are identical. Okay. So here I have some pictures and we want to decide if they're functions or not. So I'll do the first 3 and then let you think about the second 3 before we talk about them. So this first one, this function is saying if I input A, I output 3, right? Everybody see how to read the graph then? Input B, output 1, and so on. Is this going to fit the definition of a function? Yeah, it uses every domain element. And once I pick a specific domain element, there's only one path to follow. Okay, so yep. All right. What about, so I guess I should say, so this is yes. Our domain is A, B, C, D. The codomain is what? Yeah, I'm gonna zoom in. 1, 2, 3, 4, 5. And what's the range? 1, 3, 4, 5. Okay. All right. What about the second one? Is that a function? Oh, I heard yeses and nos. Okay. Yeah, it is a yes. What made you think no for a second?
Oh, because two things are pointing to the same thing.
That repeat too, but a repeat in the range is fine, right? It's a repeat from the domain that's bad. So yeah, our domain would still be the ABCD. Just going to write it this way, domain. And over here we have our codomain. But what's our actual range for this one? 2, 3, 4. All right. The third one, what do you think? Function, yes or no? No, what goes wrong? Yeah, A goes to two different things. So it has the ordered pair A1 and the ordered pair A2, and that's bad, right? Given a domain, you shouldn't have a choice. You should only go to a specific thing for that domain element. So we don't have to answer the question domain, codomain, range, because it's not a function. Okay, so go ahead. You look at the next three. I'll give you a head start. All right, the first one on this row, what do you think? Function, yes or no?
Yeah.
Yes. And my domain is ABCD, right? My codomain happens to equal my range, right? Because I use everything. And that's what we like, actually. We're going to give that a special name when we use the whole codomain. Okay. Next one, what do you say? Nope, what messes it up? That A. If I had gotten rid of that line leading to 2, would it have been a function? Yes, it'd be a silly function, it'd be a constant function, right? But those are functions. The function that says plug in X, output 3, always, that's still a function. Okay. All right. And the last one. Yes. And again, our domain is still ABCD. And our codomain equals our range. Codomain does equal our range. It just happens to be smaller than the previous one was. Okay. All right. So we got feel for a function. So here we go. We are going to say two functions are equal. We already said it means they have the same elements, but this is another way we can define that. They're equal if I have for every single thing in the domain, when I plug it in, they give me the same value. So if I let's let f of x go from the positive reals into the positive reals and define that by how do I want to do this? I guess f of x equals x squared. Oh yeah, no, let's do square root of x squared. There we go. Dang it. Square root of x squared. And we define g, so I could have used negatives, but we'll use positive, that's okay. Positives. by g of x equals absolute value of x. These would actually be the same function. Any x you plug in, it's going to output the same thing. Okay. I can even get rid of the pluses and they would still be the same function. Right? Because once I square it, it's going to become positive. So, yep. All right. Cool. So, here's what we want to focus on and what your upper level math classes will have a lot of are these three words. Okay, so we're going to take them one by one. So we have a function with domain A and codomain B. Okay, we call that function surjective, though oftentimes we'll use the word onto, if and only if. So that means for every B in capital B, every little b in capital B, there exists little a in capital A with f of a equal to little b. In common sense words, what is that saying? No, it's probably not a constant function actually. Well, so B is my codomain, right? So I'm saying take anything from the codomain, there's something that gets sent to it. You see that? Take anything from the codomain, there's something that gets sent to it. So onto surjective, you could think of it this way, codomain, yeah, equals the range. You could think of it as the whole codomain is used, same thing. All right. So we have a redrawn thing with our 6 functions. I'll zoom out so we can see them all. So which ones of these would qualify as onto? The third one. Ah, good. Not a function. So, yep. The fourth one. And the 6th. Yep. All right. So that's onto. And we'll see how to handle that with fancier functions in a second. We're just getting a feel for these right now. All right. The next word is injective. I know, sounds weird. Again, we often use a different phrase nowadays, one-to-one. Okay, so here's the idea. So F is injective, one-to-one, if and only if. So for every A and B in, well, B might confuse you. We'll call them A1 and A2, sorry. A1 and A2 in capital A. If f of A1 equals f of A2, then A1 equals A2. Sometimes you'll see this defined by the contrapositive, which would say if A1 does not equal A2, then f of A1 does not equal f of A2. These mean the same thing, right? Contrapositive and original statement have the same truth value, so they mean the same thing. The idea here, one-to-one, injective, this is where I'm getting a unique output that never repeats anywhere else. Okay, so I'm saying if I take 2 things and plug them into the function, if they're not the same, they're not going to output the same thing. okay? In high school, your teachers may have called this the horizontal line test. Now, by the way, vertical line test, horizontal line test, not valid proof techniques, okay? But they give you an idea of what's going on. They're not valid proof techniques. All right. So let's take a look at these again. Which ones would you say qualify as one-to-one? The first one. What else? Ah, the fourth one also. Okay. That second one doesn't, because both A and C, right, have a matching output. Okay. All right. So that's the ideas of one-to-one and onto, and we'll keep dealing with these more and more and more. So the last word here, it's not a big leap. Okay, so a function is bijective, and if and only if it is one-to-one and onto. Go figure. And for some reason, bijective does not get a more anglicized name or a more common sense name. It just stays bijective. That type of function is called a bijection. Go figure. Okay, so a function that is bijective is a bijection. Though, yep. So those are the most important probably class of functions we deal with a lot in math that you guys will see over and over and over, bijections. All right, so let's do more with this. So let's look at some actual formulas here, normal functions you're used to. So for each, we want to determine a reasonable domain, and we are going to use all reals as the codomain. We're going to decide if it's surjective, which was onto, and if it is injective, which was one-to-one. All right, and I left a little bit of space for us to do scratch work, though some of these won't be bad. Sine of x, is it onto the reals? No, it definitely isn't. So not onto, right? It only goes to from -1 to 1. It misses a heck of a lot of real numbers. Well, is it injective? Is it 1-to-1? No, definitely not. What is sine of 0? And what else has value 0 when plugged into sine? Sine of pi, 2 pi, 3 pi, 4 pi. It's super, super not 1-to-1. Okay. You get lots and lots and lots of repeats, infinitely many repeats. Okay. So, not. And you can start abbreviating 1-to-1 with number 1 dash number 1. It just sometimes looks like an absolute value with a hyphen in it. So just be aware of context. Okay. All right. Let's look at B. Well, it might help on B if we draw a quick little graph, because that one's easy to graph. So let me move over here. What's the graph of absolute value look like? A V opening upwards, right? If I could draw straight lines. Okay. Is this, let's start with onto the real numbers. No. What does it miss? All the negatives. It misses a heck of a lot. Okay. What about 1-to-1? No, why not? Yeah, so give me an example. Yeah, g of 1 equals g of -1. Okay. So not 1-to-1. Don't worry, we'll get some that are. Okay. All right. So let's look at C. So C, this one's a little harder maybe for you to tell off the top of your head, unless you just remember how these graphs look like, which some of you might, but let's say, pretend you don't, okay? So if I want to figure out for C, if it is onto, here's what I can do. Onto means it needs to output every single real number at some point, right? So let's let R be a random real number. Let's see what it would take to get an output R. So I need 2x cubed plus 5 to equal R. Well, that would mean 2x cubed equals R minus 5. X cubed equals R minus 5 over 2. X is the cube root of R minus 5 over 2. All right. Do cube roots have any issues, any problem spots? Good. No, cube roots are fine. If it was a square root, I might have an issue. Okay, but it's a cube root. So that, what I just figured out is that number, if I plug that into my function, that will output R. Okay, so if you say, well, I want you to output 1,000,000, I'm going to plug 1,000,000 into that and say, okay, plug this in. Plug in the cube root of 1,000,000 minus 5 over 2. Okay, say, well, no, I want you to output -13. Okay, plug in the cube root of -13 minus 5 over 2. Right, so this is actually onto. And we'll see how to prove that in a second, but we're just getting an idea now. All right, now 1-to-1. If I have, you don't need tons of space for E, so you can go down here. If I have 2 times something, so we'll say 2a cubed plus 5, being the same thing as 2b cubed plus 5. Well, let's see. I can subtract 5. I can divide by 2. When I take a cube root, do I have to worry about plus or minus or anything? Nope. So we get A equals B. So if they output the same thing, they must have been the same input for this function. That's what we just showed, right? If they output the same thing, they must have been the same input. If that had been a square or a fourth power, any even power, I would have been in trouble, right? Because I could have gotten plus or minus. So they might not have been the same. So this one is 1-to-1. All right. While we're over here, why don't we just do E? I said we don't need much space for E. What does the graph of E look like? It's just a straight line. So as long as M does not equal 0, as long as my slope's not 0, is it going to cover all the real numbers? Oh, I heard both answers. So what's the graph of a line look like? Right, it's, I mean, something like that, or maybe it goes downward, or maybe it's, but is it eventually going to cover all y values? Yeah, as long as my slope's not 0, it will. So if m does not equal 0, yes, it's onto. Is it going to be 1-to-1? Yeah. If m equals 0, well, it doesn't get either, but as long as my slope isn't 0, it is 1-to-1 and onto. So it's a bijection. Okay. All right. Now let's look at D. What do you notice about D? Yeah, it's undefined at -1. So it's going to act like what function for the most part? X minus 1. The only difference is it will have a hole at -1. So X minus 1 is, let's see if I can do this. There's the hole and there's the line. Yeah, close enough. It's not super accurate, but whatever. Okay. Is this onto? Good. It's not onto. It's so close to being onto, but it actually misses -2. Okay. Because of that hole. Is it 1-to-1? Yes. Okay. All right. You guys with me so far? Cool. So let's do an actual proof, guys. Yes.
Why is there so much space after this?
So because the scratch work will take up some space and then we got the proof.
Okay.
Yep. All right. And we're going to be very explicit because this is your first proof of a bijection. So here we go. We have a crazy function. Notice it is going from the real numbers, so that's my domain, into some set x. Well, it told me what x is. X is -1-to-1. Okay, x is -1-to-1. And this is my function. So that looks a little funny. Let's go ahead and graph that. So I'm going to go to desmos.com and graph that. Here. Nope, nope. Go this. Oh. All right.
I was like solving my computer science project. My dreams are.
When you do a lot of something, you will start seeing it in your dreams. It's true. Was that the right function there?
Yeah.
X over 1 plus x? All right. So it said it goes from the real numbers into -1, 1, right? Is what it said. And we're supposed to prove it's a bijection. So this graph seems to support that idea. Okay, that I can plug in any real number I want, but that it's only outputting stuff from -1 to 1. So seems reasonable. Okay. Just wanted to show you before. Okay. So here's how you go about doing your scratch work to prove something's a bijection. Scratch. Now, I normally like to start with 1-to-1. I don't know why. That's what I normally start with. So 1-to-1. So I need to assume two things have the same output. So I'm going to assume f of A equals f of B. And A and B are from the real numbers because that's my domain, right? All right, so A over 1 plus absolute value of A equals B over 1 plus absolute value of B. Well, before I could do much with this, I need to know if A and B are positive or negative or 0 or what. So we're going to have to split this into cases. Okay. So first, let's say A and B are greater than or equal to 0. Then I have A over 1 plus A equals B over 1 plus B. Right? Because the absolute values didn't change it because they're both already not negative. Cross multiply and distribute to get A plus AB equals B plus AB. Subtract AB. So I'm just gonna, to save space, just cross them out. So A does equal B. Okay. Case 2. A and B are both negative. What's that mean the absolute value is going to do? So how do I write it in order so it stays positive? If A is negative, what's the absolute value of A? Yeah, I put a minus that negative thing because that'll be positive. Minus a negative is positive. All right. Again, we cross multiply and distribute. Again, we have matching A, B's. They just this time are negative. So again, we're getting A equals B, which is what we want for 1 to 1. Now, case 3 would be one of each, and it doesn't matter which, so I'm going to use without loss of generality. Let's let A be negative, B greater than or equal to 0. So A over 1 minus A equals B over 1 plus B. A plus AB equals B minus AB. Now, you get into here and you go, wait a second, nothing's canceling. I'm kind of stuck. So this case, we look at it and go, but this told me to prove it's a bijection. I should be 1 to 1. What the heck is happening? So now let's go back and common sense this. If A is positive, well, A is negative, what am I going to get when I plug in A to that fraction, a positive or negative overall, if A is negative? You'll get a negative over a positive, so negative. Okay, so that means A over 1 minus A is negative. What about when I plug in B, which is not negative? He could be 0 or he could be positive. We're getting a positive or 0, right? So it's not negative. So this case is actually impossible. You will never have a negative A and a not negative B give you the same output, because a negative number can't equal a not negative number. Okay, so this case will never happen. So we're actually okay. We're still 1 to 1, because the only time I can get equal outputs, they end up getting A equal B. All right, does that kind of make sense? Okay, so that's our scratch work for 1 to 1. Now let's do onto. I need to take a random thing from my domain. What is my domain? Or yeah, my codomain. What is my codomain here? Look back. Yeah, it's that capital X, which is what? Negative 1 to 1. Okay. Yes. Correct. That's the interval. So that's the set containing all numbers between negative 1 and 1. Yep. All right. So we want f of something to equal r. So I want x of 1 plus absolute value of x to equal r. All right. So I can rewrite that as x equals r times 1 plus absolute value of x. Let's distribute the r. All right. My goal here is to get all the x's together and solve for a single x. That absolute value is in the way. I can subtract r times absolute value of x over here, but I can't factor an x out till I know what that absolute value is, whether he's x or negative x. Does that make sense? So we look back at our graph. Our graph looked like this. So if I want to output a value between 0 and 1, what type of x's am I using to get those between 0 and 1 outputs? The positive x's. If I want to output a value between 0 and negative 1, I use negative x's. You guys see that? Okay, so case 1. R greater than or equal to 0. I'm going to use a positive x for that. So we are going to take x minus rx equals r. X equals r over 1 minus r. So I skipped some algebra there, but well, one step. Factor out the x and divide. So what I'm claiming is if I plug that into my function when r is not negative, I do get out r. Let's see. F of r over 1 minus r. That'll be r over 1 minus r over 1 plus absolute value r over 1 minus r. All right. And so since r is not negative, but r is between -1 and 1, right? So 1 minus r is positive. Everybody see that? R is basically, if it's not negative, that means r is between 0 and 1 because of where r came from in the first place. So 1 minus r is positive. So r over 1 minus r times 1 plus r over 1 minus r. We're going to do this algebra in the proof, but you do get down to just r, okay? Case 2, if r is negative, so we have -1 less than r less than 0. This is where we're going to take x to be negative. So when I look at that equation I got to, I will get x plus rx equals r. X equals r over 1 plus r. And then we could check that, but we'll do that in our proof. So that is our scratch work for this. Questions on the scratch work? And I'll show you how to put it into a proof in a second, but okay, let's put this into a proof. And I know you're going, you left so much space. It's just because that scratch work took half of it, right? So, all right, so proof. Define, so we'll rewrite it. Define f from the reals into -1, 1 by f of x equals x over 1 plus absolute value of x. All right, so to show f is 1 to 1, assume f of a equals f of b for some, let's zoom out a little, for some a and b in the reals, because that's my domain. So for some a and b in the domain. All right. Case 1. If a and b are greater than or equal to 0, then f of a equals f of b means a over 1 plus a equals b over 1 plus b. So, and it's up to you how much algebra you want to write in. I guess we can write in the steps. A plus ab equals b plus, I'm running out of space, ab, meaning a equals b. Case 2, if a and b are less than 0, then f of a equal to f of b gives A over 1 minus A equals B over 1 minus B. All right, so A minus AB equals B minus AB, implying A equals B. Move that up. Case 3, without loss of generality, A less than 0 and B greater than or equal to 0. All right, so case 3, we're going to phrase a little differently, right? Our logic was a little different. Everybody with me for case 1 and case 2? Okay, so case 3, without loss of generality, A is negative, B is not negative, then f of A is less than 0, it's less than or equal to f of B, so f of A cannot equal f of B. Thus, in all possible cases, A equals B. So we showed f is 1 to 1. So that showed it was 1 to 1. We assumed that f of A equals f of B, and we showed that gives me A equals B. If our function had been something easy like a line, we wouldn't have needed all the cases, right? We just say, oh, 3A plus 7 equals 3B plus 7 and get A equals B. But this one was just fancier, so it took longer. All right. Okay, so next part. So we'll say, in order to show F is onto, consider R an element -1, 1. I know I'm getting close on space. It's all right. If, let's put it this way. If 0 is less than or equal to R, it's less than 1, then what did I use? I gotta go back to my scratch work. We used R over 1 minus R. Then R over 1 minus R is greater than or equal to 0, right? Because R is positive or 0. And so that denominator is also positive or 0 because R can't be bigger than 1. Okay. All right. And f of R over 1 minus R equals R over 1 minus R times 1 minus, or is it plus? Starting to get my minuses and pluses confused. It's a plus. Plus the absolute value of R over 1 minus R equals R over 1 minus R over 1 plus R over 1 minus R. All right, that's ridiculous. Let's multiply top and bottom by 1 minus R to get R over 1 minus R plus R. Everybody with me there? Just multiplied numerator and denominator by 1 minus R. But what does that simplify to? R over 1, which is R. So what did we just find? We still got the second condition, the second case to go, but we just showed if R is not negative, then by plugging in whatever the heck that number is, R over 1 minus R, I can output R. What would be the only issue that would make that input not exist? If R equals what? 1. Can R equal 1? No, we pulled it from that interval. So we're okay. That is a valid domain element. Okay. Oh, yeah, yeah. Just simplify this part first. It's the algebra that gets you. Yep. Yeah. As stuff gets more complicated, it's the simple stuff that trips you up because you're expecting fancy stuff. Okay. So then since it'd be super, super similar algebra, we can say similarly, if -1 is less than R is less than 0, then, and we'll just say f of R over 1 plus R, was that our correct input? Yes. F of R over 1 plus R equals R. And that word similarly is saying, yeah, you work it out. It's the same steps, basically, with slight differences. Well, if it's very, very similar, yeah, that word similarly is absolutely allowed. Because at this point, it's expected you can do algebra, right? And that your audience can do algebra. So, all right. So I just showed take any R in the codomain, I can find a valid input, domain input to get me to that R, right? What would be the only thing that would make this input invalid? R equal -1, but R can't equal -1, okay? Because that's an open interval. Okay, so thus F is onto -1, 1. Therefore, F is a bijection, or F is bijective, however you want to say it, is a bijection. So your proofs for bijection are going to have this same basic setup. You need to show 1-to-1 as its own proof, and you need to show onto as its own proof, okay? Just like with equivalence relation, you had to show those 3 separate things, okay? Here, for bijection, you just have 2 separate things, 1-to-1 and onto. 1-to-1 will always start, assume that 2 things give the same output, show that they were actually the same input. Onto will always start, take something random from the codomain, show that you can input something to get there. And it should, in your proof, seem a little magical. Like in your proof, that R over 1 minus R came out of nowhere. But we know where it came from because we did the algebra to get it in the first place, okay? So your scratch work kind of is where you do the actual work. Then in the proof, it looks a little bit like magic. Like you just pulled this out of the hat and said, this thing will get you what you want, you know? So, all right. Any questions on that? Cool, cool. Okay, so we'll keep going with functions next time.